In this video, we're going to cover areas and lengths in polar coordinates. Our first definition is the length of a polar curve described by the equation r equals f of theta, where theta is between a and b inclusive and is given by the formula, the integral from a to b of the square root of r squared plus dr d theta squared d theta. This example says find the length of the polar curve r equals e to the 2 theta, where theta is between 0 and 2 pi. In order to use the length formula, we need r and we need dr d theta. So we have r right here, and then we also need to find dr d theta. When taking the derivative of this equation, it's going to be e to the 2 theta. And then since this inside function isn't just theta, we're going to chain rule. So the derivative of 2 theta is just 2. And then I'm going to rewrite this. So we get that dr d theta is 2e to the 2 theta. So next we're going to plug this into our length formula. So we go the integral from a to b, so that's going to be the integral from 0 to 2 pi. And then it's the square root of r squared, so we're going to take this expression and square it. And then we add dr d theta squared, so it's going to be 2e to the 2 theta quantity squared. Next, let's go ahead and simplify the inside of the radical. So we multiply these powers and we get e to the 4 theta. Over here, this is going to make 4 and then e to the 4 theta. Next, this is 1 e to the 4 theta plus 4 e to the 4 theta, so we can combine those. Since this is a product, you can think of it as the square root of 5 times the square root of e to the 4 theta, and then we can bring this square root 5 to the front of the integral. And then the square root, I rewrote it as quantity to the 1/2, so now we can simplify this. We have a power to a power, so we multiply. So 4 theta times 1/2 just makes 2 theta, and now we can integrate. The integral of e to the 2 theta is just going to be e to the 2 theta, but because the theta is being times by 2, it's going to generate a 1/2 in front. So again, the integral of e to the 2 theta is 1/2 e to the 2 theta. So I brought the 1/2 to the front, making root 5 over 2, and now we're ready to plug in 2 pi minus plugging in 0. So here's our expression for the length of the curve from 0 to 2 pi. This example says find the length of the curve described by the equation r equals 2 minus cosine of theta. So you can see that we have multiple choice options and they're all decimal, so as soon as we set up our integral, then we can use our graphing calculator to evaluate it. Looking at our polar equation, this is going to be a limacone. A is 2, and then b is the number in front of cosine, so b is 1. And then when we do the ratio, it's going to be 2 divided by 1, or 2. So our ratio of a over b is equal to 2, and 2 is greater or equal to itself. So the limacone is going to be convex. And because the equation has cosine in it, the graph will be horizontal. And then also because there's a negative right here, the graph is going to be over here. So since we know that the graph is going to lie over here, a will be how far the graph goes in this direction. So we're going to go out 2. And then to figure out how far the graph stretches, it's going to be a plus b, so that's 2 plus 1 is 3. So that point goes right here. And then for this side, we do a minus b, so 2 minus 1 is 1. So we end up going out 1. So here's our polar curve. And then I made a note, it says the full length of the curve is given by the parameter interval from 0 all the way to 2 pi. So again, to trace out this entire curve, it's going to go from 0 to 2 pi. And then before we plug everything into the length formula, we need dr d theta. The derivative of 2 is 0. The derivative of cosine of theta is negative sine theta, so the negative negative will be positive. So we get that dr d theta equals sine of theta. And again, because it takes 0 to 2 pi to get all the way around the curve, we're going to go the length equals the integral from 0 to 2 pi, then the square root of r squared. So we take this and plug it in, and then we add dr d theta squared, and I'm just going to FOIL this out. So if you think of this as 2 minus cosine theta times 2 minus cosine theta, first you get 4, and then minus 2 cosine plus minus 2 cosine is going to be negative 4 cosine. And then negative cosine times negative cosine is positive cosine squared. And then we'll drop this down. So it just becomes sine squared theta. And then right here, this is the Pythagorean trig identity, where sine squared plus cosine squared equals 1. So we can combine 4 and 1, and that's going to make 5. And then I'm going to just drop down this term right here. And then using the graphing calculator, I pressed math 9, and then entered the integral from 0 to 2 pi, and the square root of 5 minus 4 cosine, and then I just put x, and then dx. And when you round to 3 decimals, you get 13.365, so our answer is C. And I just want to make a note that because from the very start we knew with these decimal answer choices we were going to use a graphing calculator, that for any future problems that you just set up the problem and then you plug it straight into the graphing calculator and get that answer. This definition says, let R be the region bounded by the graph of the polar equation R equals f of theta by the rays theta equals a and theta equals b, where f is a positive continuous function and the difference between a and b is going to be a value in between 0 and 2 pi. Then the area A of the polar region R is given by either this equation or this one. I want to focus in on this one right here. It's the integral from a to b, 1/2 r squared d theta. And then we have some power reducing trig identities here for reference. This example says, given the polar equation R equals 1 plus sine theta, find the area of the shaded region. So I just want to look at a couple of things first. We have the equation R equals 1 plus sine theta, which is a limacone. Next we have sine and it's a positive, so that's why the graph is up here. And then A is 1 and B is 1, so if you take the ratio A over B, that's 1 over 1, which equals 1. That's why the graph is a cardioid. The shaded region is right here, so it's really important when thinking of polar curves. We have this as our A, and then it continues to rotate all the way to here. So to get this shaded region, we're going to integrate from pi over 2 to pi. And we're using this formula, the area of a polar region is the integral from a to b of 1/2 r squared d theta. So it's 1/2 r squared d theta, so I drop down this 1/2, and then I'm going to plug in this for r, and then it's r squared, and then d theta. And next I'm going to plug this in the graphing calculator using Math 9. So you end up getting that the area of the shaded region is 2.178, and our answer choice is B. This example says find the area enclosed by one loop of the curve, and we have r equals 4 sine of 3 theta. So this is a rose curve. A is 4 and n is 3. Since n equals 3 is an odd number, that means the number of petals is the same value, so it's 3. And since the rose curve has sine in it, to find where the first petal is fully extended, we're going to use the formula theta equals pi over 2 times n. So that becomes pi over 2 times 3, or pi over 6. And a is equal to 4, so our petal is extended out a length of 4. And this is pi over 6. So if we wanted to finish graphing this rose curve, we could. However, it just says to find the area enclosed by one loop of the curve. So we've already graphed one loop of the curve, so we can just use this to find the area enclosed by it. So what we're going to do is we're going to find the area of half of the loop, and then we'll times that by 2 to get the area enclosed by the full loop of the curve. When we set up the integral to find the area of half of the loop, we're going to integrate from a to b. So you can see that we're ending at b, which is pi over 6, but I just want to verify what the starting angle is. Again, it looks like 0, but we're going to verify that algebraically. So one more time, again, we're going to verify that this is starting at theta equals 0, and if it is, then we'll integrate from 0 to pi over 6. But then what's happening as you rotate to this point, for example, you can see that that purple dot is the length of the curve at that angle. And as you rotate the angle more, you can see that the length of the curve is getting longer, so now we're at that second dot, and then you're getting all the way to here where the petal is fully extended. So to verify that, again, we integrate from 0 to pi over 6, what we're going to do is we're going to plug in 0 for r, because r is the length of the petal, so we just want to verify where the length of the petal starts off at a length of 0. So we plug in 0 for r, we get 0 equals 4 sine of 3 theta. If you divide both sides by 4, you get 0 equals sine of 3 theta. And then we're asking ourselves sine of what angle equals 0, and that would be 0. Since sine of 0 equals 0, then we can set 3 theta equal to 0. Therefore, theta equals 0. So we are going to integrate from 0 to pi over 6. So one more time, to find the area of one loop, we're integrating from 0 to pi over 6, but we need the entire loop, so we're going to times that by 2. So that's why I'm going to put a 2 in front. And then we're going to do the integral from 0 to pi over 6. And then the formula is 1/2 r squared. And r is 4 sine of 3 theta. All right, so we have it all set up. So first thing, this 2 and this 1/2, they cancel. Then we have 4 squared, which is 16. And then all that will be left on the inside is going to be sine squared of 3 theta. Next, to integrate this, we need to use the power reducing formula for sine squared. So sine squared of theta equals 1/2 times the quantity 1 minus cosine of 2 theta. So whatever this theta is, it's going to be cosine of 2 times that angle. So we have 3 theta, and then again you take 3 theta and you times by 2, so that makes 6 theta. So now we can take this 1/2 and pull it to the front, making 8. And now we can integrate. The integral with respect to theta of 1 is theta. To integrate negative cosine of 6 theta, because the theta is being times by 6, it's going to generate a 1/6. And then the integral of cosine is going to be sine. And then last step, we're going to plug in pi over 6 minus plugging in 0. So I drop down the 8, and then we plug in pi over 6 for theta, so you just get pi over 6. And then when we plug in pi over 6 right here for theta, the 6's cancel, and you just have sine of pi. And sine of pi is 0. So our final answer is going to be 8 pi over 6, which reduces to 4 pi over 3. This example says find the area of the region that lies inside the first curve and outside the second. We have r equals 2 cosine 2 theta, and then we have r equals 1. And we have multiple choice options that are decimals, so as soon as we get our integral set up, we'll plug it straight into the graphing calculator. This first curve is a rose curve. A is 2 and n is 2. Since n equals 2 is an even number, the number of petals is going to be 2 times 2, or 4. And because the equation has cosine in it, the first petal is fully extended when theta is equal to 0. And then each petal is going to be rotated 360 divided by the number of petals. So that's going to be 360 divided by 4, which is 90 degrees. So here's our rose curve with petal length 2, and then you have your petals rotated every 90 degrees. Next, we have r equals 1, which is a circle centered at 0, 0, and goes out 1 in every direction. And we need to find the area of the region that lies inside the first curve, which is inside the rose curve, but outside of the circle. So I shaded in that region, and you can see that if you just look at just this one part right here, if you find the area of this part and then times by 8, that will give us that total shaded region. So we're going to integrate from theta equals 0 up to this angle right here where the two graphs intersect. So we're going to solve for theta where the two curves intersect, and the way we're going to do that is we're going to use substitution. So we're going to take this r equals 1 and plug it in right here. So we get 1 equals 2 times cosine of 2 theta. We're going to divide both sides by this 2. So we get 1/2 equals cosine of 2 theta. So now we ask ourselves cosine of what angle equals 1/2? So cosine of pi over 3 equals 1/2. And then we multiply both sides by 1/2, so we end up getting pi over 6. So theta equals pi over 6 is where the two graphs intersect right here. So now you can see that we're going to integrate from 0 to pi over 6. And then the other thing that's happening is we're going to integrate the area of the outer curve minus the area of the inner curve. And the outer curve is the rose curve and the inner curve is the circle. And just a reminder, when we set up this area, we're doing 8 times the integral from 0 to pi over 6. And again, that's because we're finding the area of this section right here, and then we're multiplying that area times 8. All right, and so when we integrate, we're integrating 1/2, and then it's r squared. And remember, this is the outer curve, the rose curve, which is 2 cosine 2 theta. And then we subtract the area of the inner curve, and that's 1/2 r squared, and then the r is 1. And this is the area of the inner curve, which is the circle r equals 1. So we go minus 1/2 r squared, where r is 1. And I'm going to plug this straight into the graphing calculator. So we end up getting 3.826. So our final answer for the area of the region that lies inside the rose curve but outside the circle is D, 3.826. This example says find the area of the region that lies inside both curves. So we have r squared equals 2 sine 2 theta, and then we have r equals 1. This is a lemniscate, so it's going to be, because of the sine, it's going to fall along the line theta equals pi over 4. And then the length of the propeller is going to be the square root of a, which is the square root of 2. And then finally, this is going to be a circle with radius 1, centered at 0, 0. All right, so here's the graph for r equals 1. It's the circle with radius 1. And then we have a lemniscate or a propeller, and it lies along this angle right here. We have a length of root 2. And I shaded the area of the region that lies inside both curves. So you have this region right here, and that's inside the lemniscate and also inside the circle. Again, this angle is pi over 4. And we're going to find this angle right here where the two graphs intersect. And to solve for theta where the two graphs intersect, we're going to use substitution again. So we're going to take this r equals 1 and substitute it in right here. So we get 1 squared equals 2 times sine of 2 theta. 1 squared is 1, and then we're going to divide by 2. So we get 1/2 equals sine of 2 theta. And then we ask ourselves sine of what angle equals 1/2. So we get pi over 6. So we set 2 theta equal to pi over 6. And we end up getting that theta is equal to pi over 12. So to find the total area that's shaded, I want to just find the area of this section right here. and then we'll times that by 4, and that will give us the total area. And to take that a step further, to find the area of this section right here, we're going to take it and break it into two parts. First, we're going to integrate from 0 to pi over 12, which is this little sliver. And then we'll add to that the integral of the area from pi over 12 to pi over 4, which is this little section right here. What's important to note is this first sliver, when we integrate from 0 to pi over 12, that little section is just bounded by the lemniscate. So when we integrate from 0 to pi over 12, it's just this equation right here. And then when we integrate from pi over 12 to pi over 4, that section is just bounded by the circle, so we'll just be integrating with r equals 1. So let's go ahead and get that set up. Again, first I put the 4 in the front because we're finding that area and we're timesing it by 4. So we have the integral from 0 to pi over 12 of 1/2, and then it's r squared. But again, this little section right here is bounded by the lemniscate, which is already in the form of r squared. So r squared equals 2 sine of 2 theta, so we just plug this in. So again, we don't square this because it's already r squared. Then we add the integral from pi over 12 to pi over 4, and it's 1/2 r squared. And again, for this section right here, it's bounded by the circle, which r is equal to 1. Okay, so we have everything set up. So right here, these 2's are going to cancel. So we're just integrating sine of 2 theta. And then over here, this is just going to be 1/2. And now we're ready to integrate. The integral of sine of 2 theta, because theta is being times by 2, is going to generate a 1/2. And then the integral of sine is going to be negative cosine. And then over here, the integral of 1/2 with respect to theta is 1/2 theta. Then I just pulled this negative 1/2 right here, so then we just have cosine of 2 theta. And then same thing here, I pulled the 1/2 here, and we just have theta. At the same time, since both of these have a 1/2 in front, I'm going to factor the 1/2 to the very front. So it's going to be 4 times 1/2, which is just 2. And then we're going to plug in pi over 12 for theta minus plugging in 0. When we plug in pi over 12 times 2, that makes pi over 6. And then we subtract cosine of 0. Over here, we just plug in pi over 4 minus plugging in pi over 12. Cosine of pi over 6 is root 3 over 2. And cosine of 0 is 1. And then over here, I'm going to times this by 3 on top and bottom. So it's 3 pi minus 1 pi all over 12. Next, I'm going to distribute this negative. So we have negative root 3 over 2 plus 1. This makes 2 pi in the numerator. So 2 pi divided by 12 reduces to pi over 6. And then finally, I'm going to distribute this 2 to all three terms. So we end up getting negative root 3 plus 2 plus pi over 3. Alright guys, thanks so much for watching, and please subscribe to my YouTube channel, Math with Yosh, and hit the like button.